Hi folks, you're right. So this video is going to cover some of the concepts that are applicable across many different domains in cybersecurity. So in the introduction to CyBOK chapter, there's a section on cross-cutting themes, and as you'll have noticed when you're looking through CyBOK, that there's each main topic area has a chapter associated with it. The topics that we're looking at in this video are they apply in generally across many different areas of cybersecurity. So we're looking at security economics. So we're looking at some of the key concepts that are within the economic theory, and we'll look at a couple of examples of how they apply in cybersecurity. And so after that, we'll look at secure systems architecture, so security architecture. What we're doing here is we're looking at like high-level design of systems and how what the implications of designing a system made up of other systems, what the implication of designing systems in this way is. We'll be also looking at some of the key concepts and the best practices, with some recommendations there. And finally, we'll look at the security lifecycle. So this is in general, we're looking at how security takes place over the course of the life of a system or an organization. So we're looking in general first at the security lifecycle, and then we're looking more specifically at the secure software lifecycle. So this is a specific example of how we apply these ideas within software development. So security economics. So economic theory, why are we doing this? So we're applying economic theory to cybersecurity decision making. So economic theory provides us with a bunch of useful models and frameworks that we can use to support like decision making whilst we're within cybersecurity. So why do organizations do this? So using so all businesses, the end goal of a business is to maximize profit, and the best way to do that is to efficiently allocate the resources they have at hand, right? So when you're using an economic models, it can help guide an organization in how best to allocate the resources that are under their control in an efficient manner, and it helps the people that are making decisions remain rational when they're choosing whether or not to invest more resources into a specific area. So we're concerned with cybersecurity here. So these basically the organization needs to weigh up the costs and the benefits of investing in a specific, in this case security, but it might not necessarily be security, like cost benefit analysis, and all these economic models that we're looking at today apply for general decision making as well. So yeah, the consideration of the costs and the benefits of a security investment decision is important, and it helps us to analyse whether a specific investment that we're considering is actually suitable for a given organisation. So as an example, we would obviously expect like a vastly different security posture when we're considering something like a local bookshop or like the university library as an organisation in comparison to like, I don't know, a military base or something, for example, just as an extreme example. So the investments that the library may make and the things that may be reasonable in that context for a library to invest in, for example, maybe some like turnstile that has that detects whether books are being stolen. Like that's probably about as secure as big a security investment as you would probably need in a library. Military base, on the other hand, has wildly different security posture. They have different types of attackers. They have different threats. And yeah, they have more resources. So organizations need to evaluate how best to use their resources. And yeah, a bookshop's not likely to need the same level of security. So it's all contextual. It all depends on what the organization is and what they're trying to achieve. So cost benefit analysis is a super useful tool for, and we'll go into it with some examples in a minute, but super useful for determining the different types of trade-offs, right? So you could go for like Fort Knox level security, but it's going to be expensive, and a bookshop, for example, or a library, they wouldn't be able to continue operations and afford that. So there's trade-offs between like security, and there are a bunch of different things that security is traded off against. One is like just general like financial expense. Another is things like usability, and we go into that later in the module. So there might be, so as an example there, you've got things like multi-factor authentication, like it increases security, but it makes it slightly more difficult for the end user to engage in their like their general business operations. So yeah, there are trade-offs all over the place, and these are things that we need to consider, and we generally consider them, or businesses generally consider them, based on the monetary value. Like how much of a benefit are they going to get from investing in any given piece of infrastructure or development. So we're looking at risk assessment. So yeah, what's the this is like builds on top of cost benefit analysis, but it also incorporates methods that are like specific to handling risk, things like avoidance, mitigation, transfer or acceptance. Each of these have a different meaning. We'll be going into these the risk assessment exercise next week. You'll be looking at these in detail, but as an example, you've got like, for example, an organization may choose to avoid risk by I don't know, like not like there's a risk associated obviously with, for example, storing sensitive data on a in-house server, right? Let's just use that one as the example. If you were trying to avoid that risk, they may just choose not to store those specific pieces of data. There's also mitigation. So this might be, so in order to mitigate the damage, they may choose to encrypt those pieces of sensitive information. Or there's transfer. So transfer, they may choose, rather than handling all their own, like this fictitious organization, what they're using is an example, rather than handling their own like payment transactions or whatever it is, they may choose to outsource it to a third party. So this is transferring the risk onto another organization. Or they might accept it. They might say like, okay, well, the organization is generally saying, all right, we're fine with this level of risk with and the costs of implementing a security mechanism to try and either avoid, mitigate, or transfer isn't worth it. It's not, the costs outweigh the benefits. So we'll look at risk assessment in detail, like I said, later in the module, and yeah, you'll have a chance to perform a risk assessment in groups on a fictitious organisation of your choosing. We'll go into that more next week. Alright, so let's look at these key concepts in more detail. So cost-benefit analysis. So I've already mentioned this, but this type of analysis is very useful for decision making in general, not necessarily just for security or investment. I use this all the time when I'm making it's super useful. Essentially, all it is it's like a table. You can see on the screen. You've got a table. You've got two columns. One's for costs. One's for benefits. Essentially, what you do is you try and for a given decision that you're making. For example, let's say we were going to let's just stick with the same example. Are we storing like credit card information on our own local servers? So what are the costs and what are the benefits associated with that? There may be the costs may be your own server costs, and the benefits like costs may include like in-house training. They potentially opening yourself up to fines. You might have some benefits such as like ease of access, and like, I don't know, having records of like detailed records of specific transactions with like all the detail. There might be some benefits to it. Obviously it depends on the scenario. But then you could essentially weigh up all the costs and benefits of doing it yourself in-house, and then you can do another cost-benefit analysis of like outsourcing, for example, and they might have different costs and different benefits. So it might cost more it may cost more month to month, but it may have less upfront costs. Essentially, what you're doing is you're trying to apply a monetary value to each of these, to either each of the costs and benefits, and then you add them all up at the end, and you see to too costly, or is it actually worth making an investment? So yeah, you're trying to come up with you're trying to enumerate all the different costs and benefits that you can think of, and yeah, applying monetary values to them. And some examples, so you can think through a few of these examples yourselves. So are we gonna, let's say an organization is looking to hire a new employee in-house, hiring an external employee versus training in-house. So there are some costs and benefits associated with both of those things. Things including, like, if you hire an external, you don't know what you're getting up front. The in-house, you know what like the skill set and the pros and cons associated with a particular individual. But you're losing time on training if you're training in-house, because you're losing the time that employee would be working. Like, you're losing productivity because that worker is no longer working on what they were previously working on. Now they're doing training. Hiring an external employee, they may already have been trained in the way that you're looking for, but they're probably more expensive, or it's I don't know. There's a bunch of different things in that scenario. You could think of another scenario, for example, things like choosing between a range of different, like, off-the-shelf security solutions. Things like you might be looking for a new firewall or an intrusion detection system for your organization. There's like loads of different options. How are you going to determine which is better? Well, you can outline all the benefits of having one versus all the benefits of having the other, all the costs, etc. Other things can include, like, trade-offs between enforcing. Well, these are basically what I mentioned before. Things like multi-factor authentication or more intrusive security mechanisms that are stronger in terms of the security benefits, but less user-friendly. Things like biometrics. Maybe a high-end bank might require biometrics, like an iris scanner, but you wouldn't want that when you're getting on a bus, for example. So the law of supply and demand. All right, so this is a concept that's used to, let me move this very slightly. All right, so law of supply and demand. So we're talking about markets here. So this is going to be a bit of a crash course in economics in general. And what we're doing with the law of supply and demand is we're looking at the behavior of consumers and organizations that are operating within markets. So market is, when we're talking about a market, it's just essentially the sum total of all buyers and sellers that are engaging in economic transactions within a particular area of consideration, right? So there's markets for everything where, like, two or more people are engaged in an economic transaction. So there's a market for, like, pens, for footwear. There's that you can be broad in your definitions, like, footwear in general, or you can be like a specific type of shoe, like, I don't know, or you can say things like there are job markets. There's a job market for IT staff, just in general, or you can be more specific. You can say there's a job market for cybersecurity professionals, and you can go even more specific, like, I don't know, defensive cybersecurity operatives, or like penetration testers, or digital forensics and incident response operatives, all these kinds of things. So essentially all it is we're trying to, like, narrow down on an area of an economic activity. Anything where this, it doesn't necessarily have to be financial. There can be, like, charity work is considered economic activity still. It generates benefits to society in general. So markets can be modelled, as I've got an image on here, markets in general can be modelled using supply and demand curves. This is a very simplistic example, but essentially on the screen here you've got a supply curve which goes upwards, a demand curve which goes downwards. Where they meet in the middle is called the equilibrium point. I'll explain that in a minute. Essentially on the x-axis across the bottom you've got quantity. So what is the quantity of a product or a good or service that is being demanded or supplied, right? So in the middle, the demand for a product, whatever that price and quantity meets at, so price on the left-hand side, the y-axis, that's considered the market equilibrium, right? So supply and demand has been around for a long time. So it was popularized in the 1700s by Adam Smith, who is the father of economics. So he's the guy who wrote The Wealth of Nations. You may have heard of it. And it basically refers to the relationship between a given good and service a good or service and the willingness of people to buy it, right? So at its simplest, if the price of a good or service increases, the demand for it decreases, essentially. And the same goes the other way around. So if the price of a good or service decreases, the demand increases relatively. So as an example, you can think of like the price of a pint in a pub. As the price increases, the demand to go to the pub drops. The pubs are struggling. You can think of this anyway. There any example you can come up with yourself. So yeah, market equilibrium it just basically means that there is a point at which the quantity demanded is equal to the quantity supplied, right? So at this point, at Q1 and P1, the quantity demanded by people is equal to the quantity supplied. So if a market's in equilibrium, all the buyers and the sellers are happy. Nobody's being overcharged or undercharged. So changes in the economic environment can cause shifts in the demand or supply of a good or service. So as an example here, we're looking at, for example, defense. Let's just use penetration testers. The market for penetration testers. So the supply of penetration testing services is what we're looking at right now, right? So let's say after GDPR got announced, which is the General Data Protection Regulation Act. It basically is a law that's it had a bunch of implications for cybersecurity. Organizations essentially had to start taking cybersecurity seriously, or they'd get charged, they'd get fined like really high, hefty fines for data breaches or for not like adequately protecting their protecting data that they were responsible for holding. So as an example, when this got announced, all of a sudden a bunch of organizations which weren't previously testing their infrastructure or their applications with like security audit tests, all of a sudden they were like, oh, we need to start doing something here to tick these boxes to make sure that we're in compliance with this legislation that's about to come through. So this obviously caused a shift in the demand for pen testers, because there's all these organizations that weren't after it. All of a sudden, because of some government regulation, now there's a load more people, right? So what this does is, as you can see, the price has increased, at which the equilibrium price has increased. So firms that are providing these services can now charge a higher rate. So yeah, the price of the service has increased because the demand increased. So as we're considering like the supply of a highly skilled employee, basically a service which requires highly skilled employees, there's a long delay, and this is a problem that we run into a lot in cybersecurity. There's actually a large skills gap, a skills shortage, where there are way more jobs available than people that have the skills to actually engage in the roles. And as you'll know, it takes a long time to get trained up in order to be fully productive in these high-skilled jobs. So there's a delay between the time that the demand increases and the supply that increases in order to catch up, right? So yeah, in the meantime, security organizations are enjoying the fact that they can charge more for their services. But eventually supply reacts, so new organizations might pop up that provide the service, and existing organizations might expand their workforce due to the high price that they can command now. And eventually through like training schemes supported by the government, the skills gap will get addressed to some extent at least. So yeah, this is modeled as like a shift in the supply curve, as you can see here. So it lowers the equilibrium price a touch. So efficient allocation of resources. So this is another market concept where we're referring to how productive, how efficient production is within a market. So when the cost of producing a good or service is equal to the benefit that society gains from it, then this is considered an efficient allocation of resources. So that's what the economy is aiming towards. Okay, so return on investment. So return on investment, it's all about trying to figure out, it's related to cost benefit analysis ish. So we're trying to calculate the probability of whether a given investment is going to be worth making or not, and how much of a financial return we're expecting to make in monetary terms. So we're more or less applying the same ideas we did in cost benefit analysis, where we're comparing the cost and benefits of an investment. But we're actually trying to do a bit of math just to work out what our expected return would be based on the odds that a given investment is actually worth making. So time value of money. So this is the last one here. So this one's related to the idea that any given sum of money is worth more now than it is in the future. So this is a couple of reasons for this, but the most obvious one is the idea of inflation. So not just to briefly explain how the mechanisms of how inflation works is, inflation basically works by as the amount of money that exists within an economic system increases, each of the previous units of currency is worth less because it's more of it, right? So like, let's say there was only £1 trillion in the system. If the government decides to print more money, each of those £1 trillion is actually worth less relative to what it was before, because there's more that exists. So yeah, if they imagine they printed an extra $1 trillion, £1 trillion, whatever, you then I don't know, like it's worth half as much as it was before, essentially. So yeah, as time goes on, inflation kicks in because the government is constantly printing money. They call it quantitative easing, because don't want to advertise this too widely, but yeah, it's been going on for a long time. And essentially, yeah, inflation, we pretty much have to live with it at the minute. It leads to an increase in the price of goods and services because your pound is worth less than it was before, so you need more of them to buy the thing that you wanted before. The purchasing power of your money drops over time. So that's one reason. There's another reason, there's a bunch of other reasons, but another reason might be that you are actually gaining some economic productive value that you wouldn't. Like, let's say you were going to invest in a new, a new system, any kind of system. Let's say you needed a new software system to manage your business. If you bought that today rather than in 2 years' time, you're going to get 2 years worth of value from it that you may not necessarily have got immediately. If you were messing around for a while trying to determine which one to get, you're missing out on potential productivity. Okay, so let's have a look at security architecture then. So when we're talking about architecture in relation to systems, we're actually talking about the high-level design. So you can see on the screen, I've got a diagram that I found online. This is just an example by Prakash from 2021 of a web application, an architectural diagram for a web application that they designed. So if you look into systems architecture, you'll see diagrams that look something like this. It essentially like tries to group the different system components and show mappings between how they relate to each other and how they interact. So security is it's not something that you can effectively implement as an afterthought. So best practice when we're talking about security design is to actually treat security seriously from the initial design conception stage. When you're first coming up with the idea for a system, you should consider the ways that the like negative security impacts, the threats and vulnerabilities that are related to that system when you're designing it, and security should be built in from the ground up. The reason for this is it's very expensive and it's very difficult to retroactively, so after the fact, decide that you want to make a system secure that you didn't have any concern about initially. So this might be due to issues where some of the system design features are just like inherently insecure and not designed to be used in the way that they are later used. So for example, there are a bunch of systems that exist that were designed before the advent of the internet, and they all had to be like updated after the fact to deal with the fact that they are now connected to a worldwide network of other machines, when originally everything that was designed on that system was designed with the idea and the context, the idea that it would exist within a context that was not networked. So that's an example of some of the issues with not considering security implications of systems up front. So when we are designing a secure system, we need to ensure that we fully understand all the elements of the system before we start writing any code, essentially, or building any system, depending on what the system's constructed out of. It might not necessarily all be code. It could be a cyber-physical system where there are like actual sensors and stuff. We need to basically understand the context of what the system, the environment that the system is going to operate in. We need to also consider how that may change in the future, and we also need to consider not just how a system should conceptually operate. Like we might say, all right, we need the system to do A, B, and C. There's always one area, like one of the main areas in which bugs and security problems can emerge is in this difference between, and we'll go into this a lot in other modules, specifically in the exploit development module at level 7, but we essentially the difference between what the designer or developer intended the functionality to be. So we want this system that can do A, B, and C, and only A, B, and C. We don't want it to do anything else. The difference between what they actually, the desirable traits of a system versus what the system can actually do in reality, yeah, this is where bugs and security problems generally emerge. So yeah, you need something we should be concerned about is being specific about our design requirements. So next thing we need to consider, so this is one of the main ways that this is done in practice, is essentially we want to compartmentalize the system. So what does this mean, and why are we doing it? So why we're doing it is to try and make life more difficult for a potential attacker. So an attacker, either internal or external. If we're using a compartmentalized design, which essentially just means that we're splitting up the different roles and responsibilities of different parts of the system and different users on the system. So I'll go through a couple of examples in a minute, but we're essentially trying to limit any damage that an attacker, either internal or external, we're trying to limit the damage that they're able to cause if they were to successfully cause a breach to the security or anything like that. Let's say they have access to a specific user's account. So I'll give an example, I guess, and this is related to the stuff that we covered in the principles video, right? So we discussed in the principles video two principles that are super related to this. Is like the separation of privilege. So that's all about splitting up the application or the system into components and limiting what each of the components can do. So that's related to the principle of least privilege, right? So we're trying to give either a system component or a user on a system, or a user with a given role on a system, the least amount of permissions that we can give without them, whilst giving them the ability to still like operate in their daily business role. So for example, you might not necessarily, it might at some organizations they may not have these like access controls in place, or this compartmentalized design, and it may be possible, for example, for like a receptionist or a secretary at a business to have like direct data, write access to a production database, for example. Something that you probably would never, you would never need to be able to, the secretary to be able to do that. So if we're thinking about secure design and like limiting the damages that that could occur if, for example, that secretary's accounts got compromised, or someone socially engineered that secretary. We're trying to design the system in a way that it limits the damage that can actually be done if any given component in the system gives way, I guess. If any given component gets compromised, how do we ring fence the damage? So the same goes again for network, at the network level and like the data design level. So we don't really want, for example, a application that might manage I don't know, let's just say, for example, there's a web application and there's a form where users can change their address or whatever. This might be, you want to kind of ring fence this so that it's not also, like, this application is not connected to everything else. It's only connected to the thing that it needs to be connected to. So yeah, this is all in line with the goals of maintaining data integrity, confidentiality, and accessibility, the general security goals in the CIA triad. So we also, another part of security architecture, more modern security architecture, is actually like doing active detection of anomalies and threats. So what we're doing here is we're actually, this is more about the way that the business IT infrastructure is designed. So in this way, we'll be, in order to detect anomalies and threats, we're looking not only at, well, there's like a two-pronged approach, right? You're looking at the content of network traffic, so things that are coming in and out of the environment, and things that are happening internal to the network on different network segmentations and layers. So we're monitoring, we have tools and systems that are monitoring network activity, but they're also monitoring system activity as well. So there might be audit logging systems that are running on like the workstations of an organization. You may have some kind of tool on there that's checking what the users are doing, which files are they opening, are they trying to run programs or interact with resources that they're not supposed to interact with. So there are things are they operating out of hours? So let's say that, so this is in line with anomaly detection. There may be some machine learning or some AI tools that are used to determine what the typical activities of a particular user of a given role would be, and if they start wandering outside of those, like for example, they might start transferring like massive amounts of, like exfiltrating huge amounts of data, or trying to like over the network at like 3 a.m. or something. So basically there are tools and systems in place. They generally fall under SIEM, so that's Security Incidents and Events Management, or SOAR, which is Security Operations, Automation and Response. So these things are essentially tools which collate and manage log activity and audit activity over networks and systems, and do some processing on it to determine whether there's anything, whether there are any threats or anomalies that need looking at. They usually like raise a flag for someone who works in a security operations center to actually have a look at and investigate. That's all within the SIEM section. This SOAR builds on SIEM by automating the response. So rather than just flagging up an alert and saying, hey, can someone look at this, it might be that the system automatically like disables an account if it's doing certain things which look too suspicious. It might just automatically shut that account down, and everything that's associated with that user account is also all shut down, just to try and minimize the damage. It may also be like to switch firewall rules, or the automated responses are context dependent. So security architecture. So we're going on to requirements and threat modeling. So requirements. What we're actually doing here, first stage. Sorry, my head's in the way of the reference. A little bit over here. So yeah, the first stage is to define what the system should do, and to formally outline the security requirements. So what we're doing here is we're describing the system's capabilities and like the boundaries and the limitations. So what should it be able to do? What shouldn't it be able to do? So all of these kinds of questions that we're looking at here. So this should take place before the implementation phase. So in a couple of slides time, we'll go through the lifecycle phases. But yeah, essentially, you come up with the requirements, then you implement testing, verification, etc. Come up with response plans. It depends on what level of analysis you're looking at. Are you looking at the life cycle of cybersecurity within an organization, or are you looking at like something more specific, such as the life cycle within like a software development, secure software development process. So these are the slightly different processes. So threat modeling. So threat modeling, there should be a model at the design stage. Before you implement anything, you should come up with a model of the system, as there's an example here, which is essentially outlines the trust boundaries. So trust boundaries are essentially placed in the system where the level of trust changes. So for example, in this example, we've got like a threat model of a college library website. The trust boundaries are the curved dotted red lines, and essentially these are there's two trust boundaries here. There's one between the web application and the database, which is the vertical one, and there's another between the end users and the web application. So if you outline the reason we're outlining trust boundaries is because these are areas which extra care or consideration should be taken when you're thinking about data validation. So these are places in the system where untrusted data could potentially enter the system, right? So we don't necessarily know what the user can do. If we're designing, for example, let's say we're designing this college website, we want to basically limit what the responses that the application has when different types of data come to it. So we want to validate the data that comes in. Let's say that they're trying to log in to a web application. They might be passing in a username and a password. At this point, we basically want to make sure that they're not just putting that the data that they pass into the form and into those fields that hit the web application. We want to make sure that we're not letting that we're validating the data before we use it. So this is an example of why this might be useful or why this is necessary is you can think of like SQL injection or any command injection attacks where basically the user these types of vulnerabilities are ones in which the server basically doesn't validate the input. So the input might have special characters in it that get interpreted as code or commands, and we don't want that to happen. So we need to make sure that before we're using any of this, basically we need to design the system in a way that data that's input across trust boundaries, or any data that crosses trust boundaries has been inspected, so that there's nothing in there that's going to make our application do things that we don't want it to do. And yeah, some related vulnerabilities to look at if you're interested are things like SQL injection, cross-site scripting, or any kind of command injection attack. These are things where you're inputting into a form, or you're passing data into an application that contains like commands or characters that the application interprets as code, and then you can get that application to do things that it shouldn't do. Okay, so how does it all fit together? So NIST, which is the National Institute for Standards and Technology, it's an American organization, US government affiliated organization, which they provide standards for technology, and they're used widely in cybersecurity. So this is their framework, their cybersecurity framework, and it provides 5 different functions which are often framed in a life cycle. You can see the diagram above. Essentially, you've got the identify phase, which is all about identifying assets that are under management or that organizations have. So this is surprising sometimes that organizations don't necessarily have they don't necessarily track and monitor all of the assets all of the technical assets that they own. There are sometimes there are difficulties sometimes with legacy organizations that have been around a while that have loads of systems in different warehouses and all over the world. They struggle to actually get an accurate map of what they own and the things that are connected to the networks, things that all these different systems and how they interact. So first step is identifying what you've got and the current state of the systems. So this might be doing things like checking if what versions of software you've got installed on all of these different systems. What operating system are you using? Are you using anything that's out of date and has known vulnerabilities? You want to see, you're basically taking stock, what do we have here? You're also identifying things like the risk assessment and management processes and risk governance. We'll talk about that a lot in the next video. Then next is protect. So the protect phase. So this is all about like keeping your assets secure. So you're doing things here like looking at and implementing access controls. You're doing awareness and training. So giving staff members training in cybersecurity, risk management, anti-phishing, anti-social engineering stuff, things that are relevant to whatever role they're in. So you've got data security. So are we encrypting data? How are we like sensitive information that we're storing? Are we handling that correctly according to the rules and regulations and law that's in place that sets the limits for what we're allowed to do and what we're not allowed to do with regards to sensitive information. So then we've also got defensive mechanisms. So at the protect stage, you've got things like I just mentioned. We just talked about the anomaly detection and like system monitoring. So you might have intrusion detection systems. You might have like firewalls. What have we got in place? Have we got multi-factor authentication, or do we have a single sign-on service? Do we have like, what's our password policy? Are we enforcing regular changes of passwords, cycling? Not allowing people to reuse old passwords, making sure that they're complex and not crackable, they're stored in a secure way, so salting and hashing rather than just plain text. Anything, all these things come into the protect phase. And we've also got things like, in the protect phase, we've also got things like automated processes and procedures that are in place to try and keep things more secure. For example, like automated regular patching, things like that. So the next phase, we've got detect. So this says detect incidents. So this is actually talking about as business operation is, it's just like throughout everyday usual business operation, what are we doing here? So we got like, this is more related to the monitoring stuff. So we've got like intrusion detection, system monitoring. Do we have anomaly detection and threat detection? Are we using SIEM and SOAR systems? Then you got the respond. So the respond with a plan. So this is all about incident response planning, things like digital forensics and incident response. Do we have like backup? Oh, well, actually, that comes into the next phase actually. So we've got, this is all about planning for how to deal with an incident that's happened. In the previous phase, we've detected an incident. Now what are we doing? So this can involve things like analysis of what happened, trying to mitigate and improve on this, mitigate against this happening in the future by introducing improvements to the system to shore up any security holes, or like what caused it. Is there any way to prevent that from happening in the future? That's what we're aiming to do here. And the next phase is the recovers phase. So this is recovering normal operations. So if we have had an incident and we've responded to it, we've figured out what's gone on, how do we get back to normal business continuity? So this is things like, do we have failover systems, like contingency planning? If like what do we have in place if the network goes down? What do we have in place if power goes down in a building, an office, for example? What happens if a web server goes down, our main web server? Maybe we've got a backup, something to fall over to do. We're also looking at backups, like backups of data, database backups, anything that's used in business operations. How do we recover from? So do we have a plan in place to return our data back to the form that we had it in before using a backup? Or how do we improve on the current systems? So that all takes place in the recovery section. So that was looking at the life cycle from an organizational point of view. How do we, as a holistic organization, handle security over time? Now this is more specific, right? So we're looking at this is the Microsoft SDL. So the SDL is a security development lifecycle, and this is a methodology or framework that has been created and used and supported by Microsoft, and it's for the development of, it's a model to follow for the development of secure software applications. So lifecycle starts with training. It goes training, requirements, design, implementation, verification, release, and response. So we start with training. So this is all about developing the skills. This is pretty straightforward. Developing the skills and knowledge of like cybersecurity that's required to construct a secure application, or to use the application, use security features of the application, etc. So after this, yeah, that's pretty self-explanatory. So requirements, we've got establish the security requirements of the system. So as this is basically, we've covered this briefly before, so this is how the requirements specification comes into the picture. So this is things like, as an example, you might say like one of the requirements is that unauthenticated users should not be able to access a private members section of the web page, for example. And authenticated non-admin users should not be able to access the admin page, stuff like this. It's like setting out the outlines. What should the application be able to do? And when we're talking about from a security perspective, we're saying like things like that. Things like setting up boundaries, access controls, things like that. Not just that. Obviously, we're looking at like mitigating against vulnerabilities as well. So we're validating input across trust boundaries, things like that. So these are all like should statements or should not. So the system should do X or should not do X. X user on the system should be able to do Y, stuff like that. So create quality gates and bug bars. So quality gates and bug bars are a way of like specifying what the accepted level of the accepted level of bugs or security problems within within the system should be. So when you're creating a system, as you probably know, doing a bit of programming at this point throughout the course, and probably some in your own time as well, you'll know that bugs are probably inevitable. In most cases, it's very difficult to design a system that's flawless and has no problems. It's even more difficult to implement a system like that. Even if you had a perfect design, it's very difficult. So some bugs are probably inevitable, and there might be like an acceptable level of non-security related bugs. So as long as they don't necessarily impact any of the security goals of like data confidentiality, integrity, or availability, they might be acceptable. So they set a level. That's just requirements are just basically setting what is the acceptable level of flaws within the system if we're going to release it. Risk assessment. So security and privacy risk assessment. We'll talk about that in the next video in detail, but this is essentially just like identifying what the risks associated that are related to information security are associated with such a project. Not just information security, privacy as well. It's all kind of falls into the same area. Then we've got the design phase. So as we covered in the architecture, we're coming up with some system requirements. We're outlining the attack surface. So this is going back to the previous diagrams with the threat boundaries. The threat model diagram and also just the architectural diagram. We're outlining the attack surface. So what's the attack surface? That's basically, we can think of that as all of the potential areas that an attacker, either external or internal to the organization, is able to interact with the system. So where can they interact with the system? These are all areas where they could potentially attack the system. So for a web application, this might look like a list of all the domains and all the subdomains, any files or directories that are stored on that particular web server that's being hosted. Then you've got things like anywhere you can send HTTP requests, and any parameters that you're sending across. So things like, if you, for example, I used before, it was like posting a username and a password to an application login. When you're coming up with the attack surface, you're basically looking at where can an attacker interact with this application. So for the example I gave before, we were talking about the attack surface of the actual web application, but also the web application will be running on a web server, which may have other ports open and other services running on it. So that's also part of the attack surface, because if you can get into the server and you can access the database, then you've compromised the the system. So yeah, that's we're also looking at threat modeling. So that's what we talked about before. But yeah, this should come at the design phase. So before anyone starts writing any code, we should understand where all the trust boundaries are. So we've got a next implementation phase. So this is where we're actually building the system based on the requirements and the design that we've come up with in the previous section. Phase, sorry. So here, diagram talks about using approved tools. So as an example, this might be using a trusted compiler, which has security options enabled. You might outline the things, the tool chain that the developers are using throughout the process, and yeah, you don't want them to use. They're using it like with the compiler example. Yeah, you need to make sure that you trust the compiler, because that's the thing that converts the code from a high-level language into machine code that actually runs. And if you don't trust the compiler and someone's like tampered with it, the instructions that get output might not necessarily match the code that you put in. There might be like some hidden behavior in there, like a backdoor, for example, that's been inserted from like a dodgy compiler. So essentially we want to make sure that we're using approved tools that have been reviewed and audited. Deprecating unsafe functions. So what we mean by this is some programming languages and libraries include functions that they're there for legacy reasons. They might not necessarily be secure, but they're kept in for like compatibility with old applications. So these are things that should be avoided, and if we're using them anywhere in our application, we should deprecate them, which is to basically allow their use but warn the developer that they're unsafe, and strongly discourage the use. But yeah, they are technically able to be ran. And static analysis. So we're talking about static analysis it's a technique for automatically. So we do a lot of this in reverse engineering. Static analysis is basically just like running analysis tools on source code, so you're not actually you're not compiling the program or interpreting the program and running it. What you're doing is you're looking at the actual source code and running tools that look at it and say, oh, this is potentially an area where bugs may appear, or this is potentially could lead to a security problem, the way that this particular code has been written. So that's what static analysis tools are. They're used as you're developing. You run this static analysis tool as you're building the software, and it'll come up saying, oh, maybe you want to look at this, maybe this is a problem, maybe this is a problem. Okay, so verification. So this is essentially like testing and quality assurance for the system. So at this stage we do dynamic analysis. So this is similar to static analysis in the sense that we're trying to detect program flaws, but instead of analyzing the code, like just the code at rest, we're actually running the program and we're looking at the behaviors that the program exhibits during the course of execution, rather than just trying to infer from the code problems. We're actually running the code and we're seeing, all right, what can we do here? So fuzz testing is an example of this, and this is something, again, we'll cover this in detail in level 6. You'll be doing some fuzz testing in the system security module. But fuzz testing is a type of dynamic analysis where we're giving randomized or basically procedurally generated inputs into a program. So we've got a program running, it accepts a username and we'll just stick with a super basic example we've been doing before, like, yeah, you've got a web page with a login form, right? It's got 2 inputs, a username and a password. What we're doing in fuzz testing is we're trying to put in lots of procedurally generated data, which is either random or formed based on known bad inputs. So if we were testing that form for specifically for an SQL injection, we might input things like semicolons or double quotes, things that would break the SQL command. But if we don't know what we're testing for and we're fuzzing it, we're just trying to essentially pass it as much different types of inputs as we can to see how we can break it. Essentially, we're trying to get the thing to fall over and break, so it can be like, there, that broke. That broke with this input, which was this long string that had a bunch of different characters in. Why did that happen? So then you can go and fix your problem, rather than releasing the application without doing any fuzz testing, and someone comes and manually discovers that there might be a particular problem with a certain given input, you're trying to just feed it as many randomized inputs as you can to see, not just to see what happens, to try and break it. So attack surface review. So yeah, we're looking at whether the attack surface that we expected in the design phase, see if that actually maps onto reality. After we've implemented it, we're basically saying, all right, this was the design with the threat boundaries, and this is the attack surface that we thought we had. Actually, when we implemented it, we realized we needed these other things in order to make this requirement work. We needed these other functions, and the attack surface may have changed. So you want to check that and make sure that you've got a good understanding of the areas in your application which can be attacked. So then release. So at this point, you're releasing the software product to the customer or to the end user. And at this stage, yeah, you need a plan for how to respond to incidents. So we'll be covering this next year again, incident response and incident response module. It's all about how do you react when a problem, you've had a security incident. How do you find out what's happened? So there's some forensics components involved in this. But at this stage in the SDL, we're talking about creating a plan for how to deal with an incident after the fact. So this might be, yeah, things like restoring backups. How do we ensure business continuity? Yeah, etc. So we've also got a security review, and a creation of a release archive. So this is just doing an overall final review of the security of the system. And a release archive, we're essentially there. We're just keeping a version of the software that we've released in an archive or repository for future, so that we have a copy of the exact system that we released at that time. And keeping archives, yeah, it helps in future. You may come back. You may have like some software companies have different versions of this systems for different clients or companies. Yeah, keeping a record of exactly which version different people are using at different times will help you in the future when you have a problem with one customer. Might be like, oh, I've got this issue, this only affecting them, nobody else, and then you go back and you say, oh, well, they're actually using this version which had this specific feature that they wanted but nobody else did. And yeah, it just helps you keep track of the state of your application and how people are using it, the different versions. And then, yeah, okay, so the final stage, yeah, we've got response. So this is the stage that kicks in if there has been an incident, and at this point we're just executing the incident response plan. So we devised this plan in the previous release phase. Okay, so that's everything for the cross-cutting themes. So just a quick recap, we've looked at the way that we can apply economic theory in cybersecurity. So we've done things like looked at cost-benefit analysis, we've looked at the law of supply and demand, and market forces in general, and markets. Then we've looked at what we mean by an efficient allocation of resources, return on investment, and we've also looked at the time value of money. And then we looked at security architecture, so we just had a look at the high-level design of systems and how we model threats, identify areas in the system in which trust levels change, which may be worth considering, worth more consideration from a security point of view. And then, yeah, we looked at the security lifecycle and phases. So we looked at, in general, we looked at the NIST framework for the cybersecurity lifecycle within an organization. Then we looked more specifically at the Microsoft Secure Development Lifecycle, which is a framework for developing secure software applications. Thank you.